All right, everybody, I'm ready to get started. Welcome back. Today's not the 6th of October. I forgot to change the date on this slide. But welcome back, everyone. Welcome back to 308. End of the 6th week together. Like I said last time, we're nearing the halfway point. I think we have about 2 weeks left before spring break. So there's like a spring break in there. That's just kind of like shoehorned into the middle of the semester, which is weird, but hey. It is what it is. I believe the second exam is after the spring break, so you'll have some time to kind of, gather yourself after, the storm of midterms that you've already been through, and kind of have a moment to kind of think about like your plan toward, moving towards the end. What I'll do for chapter 5, 6, and 7 that we'll cover next week. Is I will make the due dates for them. Well, not 5, but 6 and 7. I'll make the midterms for the mini papers due after spring break, so you'll have time to work on those. We'll start working on chapter 8 prior to spring break, and then finish it after that, and then that'll finish the material for the second part of the course, and then the exam will be pretty immediately after that. So even though spring break is a break, it shouldn't be a break from school. Like, just reserve that time for summer. You're going to get 3 months. Enjoy that time. It's an opportunity for you to just really immerse yourself in what you have to learn to do really well this semester. Get ahead, get caught up, whatever it is that you need to do to make this work out in the best way possible. It's an opportunity to make that happen. So make sure you make that happen during that time. Of course, squeeze in a little bit of fun, definitely. Enjoy your lives, but you must make this the priority. You have to make this the thing that you do all the time. And if you do that, things work out well, and then you wind up being very satisfied overall with how things are going, and it makes everything else very enjoyable. Specifically, 3 months of vacation. Where you're not harboring guilt and resentment and whatever else because you didn't put in as much as you could have during the semester. So anyway, I'm going to try to make it, an opportunity for you to, at the very least, knock out some of the mini papers if you haven't already, so that you can at least have that portion of the course out of the way, and then just, focus on the material, focus on your other classes, and make this whole thing work out. Are there any questions about anything before I jump into today's material? All right, folks. Then today we are continuing on with Chapter 5. We won't quite finish Chapter 5. There's one section of Chapter 5 that we'll cover at the beginning of next week on Tuesday, and then we'll also cover Chapter 6, because Chapter 6 is not that long and it's not that complicated, so we'll just knock that out on Tuesday as well. So I have already opened up the homework for this chapter, though, and once we're done today, you should have everything you need to do that homework if you want to get it done, but the due date won't be till a week from Sunday night, so you have some time to work on it. But like I mentioned last time, we're going to cover chapters 6 and 7 next week, and so you'll have homework for those as well, so you might want to just start knocking this homework out and then chapter 6 out sooner rather than later as well, so it doesn't all kind of pile up on you. Maybe I'll give you a couple extra days for the 7 one. I'm sure I will. We'll talk about it next week. Yeah, so that's kind of the plan moving forward. So we've been talking about production, and now we're going to relate it to costs, which is ultimately what this whole chapter is about. It's like laying the theoretical framework that we need to provide the intuition that's necessary in order to then be able to analyze optimal decision making by managers in different contexts that industries might find themselves in that will differ with respect to how competitive they are. And so in order to have any kind of sound sort of principles that we can extract from all of this, we need very solid foundations of ideas to support it all, and that's what this is about. In order to establish the nature of cost, you have to establish the nature of production. We did that. Talked about the production function. We talked about the production function in the short run, in which at least one input into production is fixed. And we talked about the optimal selection of the one variable input into production in the short run, which is assumed to be labor, via that condition of setting the value of the marginal product of labor equal to the wage, the extra benefit of hiring a person equal to the extra cost of hiring a person, the marginal benefit equal to the marginal cost. In the long run, things get a little bit more complicated though, because in the long run, everything's variable. So then the question is like, how do you optimally select the inputs when everything can be changed in order to minimize costs, which effectively will maximize profits? So that's what we're doing now. We're examining the framework that allows us to identify that optimal condition. And it's similar, like I said, to the rational consumer choice model, mathematically, in the sense that it's a three-dimensional relationship between production and two inputs that can be varied, labor and capital. And so you have a similar framework to what we had with the utility function and the indifference curves, and the budget constraints that allowed us to establish the optimal choice of a consumer when they're maximizing their utility subject to a budget constraint. The framework is similar in terms of how it works, but in terms of what it means and the logic and intuition that you gain from it, it's applied specifically to production. And the approach is that a firm is looking to maximize their output at the lowest cost possible. And so that's what this whole framework is about. We started developing it last time. With the ISO quants, which are like the indifference curves. So I'll briefly go over that. Then we'll throw in the budget constraint, as it were, for a firm, which is called an ISO cost line. ISO, same cost, basically representing the varying combinations of the inputs that can be used to produce at the same cost. And so interacting the ISO quant, same quantity, curves with the ISO cost curve gets you to that optimal selection of inputs in the long run that will minimize costs. And then the condition that comes from that is what's most important, and then we'll do a quick sample to kind of highlight the nature of that. And then we will jump to cost. We'll kind of connect it all to like how all of it implies something about like a cost function, and how all the various properties of production that we've assumed imply a lot about the nature of costs that firms face in general that will be relevant to optimal decision making. And so by the end of today, we'll have all that framework down, and then we can start talking about the applications of that information as we move forward. So yeah, cost function will be the last thing we cover, and then there's a multi-output cost function application, which is what I'll cover on Tuesday, where a firm is producing multiple goods and services, not just one type, and so there's certain characteristics that the firm can exhibit with respect to those production processes that will help them to either minimize costs by producing them together, or maybe like producing them separately. You can get that information from the nature of the cost, which we'll talk about. Anyway, so previously we started talking about ISO quants. An ISO quant defines a combination of inputs, capital and labor, that yield the producer the same level of output. Again, they look like indifference curves. We generally will always plot capital on the y-axis and labor on the x-axis. And so you have sort of a trade-off as you move from left to right, as you substitute capital for labor. And if you're on an ISO quant, same quantity, then the different combinations of the two inputs along that curve will yield the same amount of output. So this ISO quant represents all the combinations of capital and input that will yield 100 units of output. And as you get further away from the origin, the ISO quants represent combinations of the inputs that will yield higher levels of output. So this one over here, if you have a lot of capital, a little bit of labor, you'll be able to produce 300 units of output. But if you also have less capital but a lot more labor, you'll also be able to produce 300 units of output. And the slope of the isoquant is known as the marginal rate of technical substitution. Again, the analog to the slope of the indifference curves, which were the marginal rate of substitution. Those were equivalent to the ratio of the marginal utility of the good on the x-axis to the marginal utility of the good on the y-axis. So similarly, as far as like the underlying mathematics of the whole thing, it allows us to express the slope of the indifference curve, the isoquant, as being the ratio of the marginal product of the input on the x-axis, which we assume to be labor, to the marginal product of the input on the y-axis, which we assume to be capital. And so what the marginal rate of technical substitution tells us is the rate at which a firm can substitute one input for another in order to maintain the same level of output. And depending on the type of production process, you may have a situation where that is constant, where that actually doesn't play a role at all, or that is changing along the isoquant. So the example where it's changing along the isoquant is the most common and is reflective of that cost function that the production function that we've been establishing is the most common case, which is the Cobb-Douglas production function. But we also mentioned that you could have like one type of process where like it doesn't matter how much capital or labor you're using, like the rate at which you can substitute them will be constant, and that is captured by a linear production function. So the linear production function implies isoquants that are just lines. Their marginal rate of technical substitution does not change, regardless of how much capital, how much labor is being used. That's because the inputs into production are considered perfect substitutes. So you could potentially just use labor or just use capital to produce what you're trying to produce and maintain the same level of output. Again, the inputs are perfect substitutes for each other, and the rate at which the producer can substitute between the inputs is independent of the level of input usage. So we know for the linear production function that looks like this, if we take the partial derivative with respect to capital, so if you take the derivative of this with respect to capital, remember, if you're taking a derivative of a function that has more than one variable, you assume the other variable to be constant. The derivative of a constant is 0, so this drops out. The derivative of this is equal to what? A, right? It's just equal to A, just the coefficient on K, which is A. So the marginal product of capital is equal to A, the marginal product of labor is equal to B, and we know the marginal rate of technical substitution is the ratio of the marginal product of labor to the marginal product of capital, so the marginal rate of technical substitution is equal to B over A, which is constant, which is independent of the level of labor and capital used. All right, so that's the linear production function case, and then we have that other extreme sort of end of the spectrum of what a production process could be in terms of the substitutability of the inputs into production. And this is a case where they're not substitutable at all. They're actually complements to production, the inputs, capital and labor. They have to be used in fixed proportions, and that implies these right angle isoquants. And the reason why they have right angles is because if you imagine just a situation where, like what we were talking about with the example we highlighted, where like, it's a word processing firm and it's only like one typewriter or whatever computer per person, and that's the only way you can increase output is by increasing both inputs in the same proportion, 1-to-1. So if you have, let's say, a certain level of labor and you were to just increase your capital a bunch, it's not going to increase your level of output at all. And if you have a certain level of capital and you increase your labor a bunch, it's not going to increase your output at all. You need to increase them both in order to increase your level of output, and that's why you have those right angle isoquants. Again, this is representing the Leontief production function, which again is kind of like not a common case of production, but it's kind of at the opposite end of the spectrum of what it could be in terms of how substitutable the inputs into production are. So inputs must be used in fixed proportions, so the manager cannot substitute between capital and labor and maintain the same level of output. There is no marginal rate of technical substitution for a Leontief production process. because there's no substitution amongst inputs along the isoquant. For most production relations, the isoquants lie somewhere in between the perfect substitute case, the linear production function case, and the fixed proportion case, the Leontief production function case. So the Cobb-Douglas production function falls into the in-between case and is the most common. And so the isoquants have this convex shape. And what that means is that the marginal rate of technical substitution is diminishing from left to right. The reason for that is because we try to add a little bit more sort of realism into the model by saying that earlier inputs into production that are labor are going to be more suited to the production process than later inputs. So, there's going to be people that are suited for whatever is being produced. They're good at it. They've been doing it forever. They're going to be very efficient at what they do. And so they're going to be worth a lot in terms of like the trade-off between them and capital necessary to maintain the same level of output. But as you hire more and more people, you need to hire people that aren't so, specific to your process. They need to be trained. They need time to get really good at it. It might take years, so the bigger the production process gets as far as labor, meaning the more labor intensive it gets, meaning more labor versus capital is being used, then the trade-off between labor and capital to maintain the same level of output becomes less, because the value of labor in terms of capital that will allow for your output to remain the same is going to be very small, because that labor is not worth much in terms of like what they can offer your overall production process, because they're not that great at it. And so because of that, you have a diminishing marginal rate of substitution from left to right. And then you can think of it the other way as well. So like this laborer here, if we were to subtract that laborer, then we could replace them with 1 unit of capital in order to maintain our output at 100. So the marginal rate of technical substitution would be 1 there. But if we were to get rid of this other laborer, which is closer to the origin, meaning that they're more suited to the production process, then the trade-off between that person and capital is going to be 3 units. So the marginal rate of technical substitution in order to maintain the same level of output is going to be 3 to 1. So in order to getting rid of that person, you'll need 3 units of capital in order to maintain the same level of output, versus this other one where you only need 1 unit of capital to replace that one person. Again, this is just a simple numerical example just to highlight what it means to have a diminishing marginal rate of technical substitution. Yeah. In absolute value, we're talking absolute value. Oh yeah, but like I'm just highlighting the nature of the isoquant and like what it means to have diminishing marginal rate of technical substitution. I'm not being like super specific about like the math with respect to like the relationship. That would require like an actual like equation and data and whatnot. Yeah, this is just meant to get you to the intuition you need to understand it. So this production function satisfies the law of diminishing marginal rate of technical substitution. As a producer uses less of an input, increasingly more of the other input must be employed to produce the same level of output. All right, so that's the isoquant part of the long run production function model. The other part is the iso cost. It's the limitation that the firm faces. Either they have a budget that they're trying to satisfy to target a certain amount of output, or they're trying to minimize the cost of producing a certain amount of output. So the combination of inputs that will cost the firm the same amount comprise the iso cost line. Again, it is the analog to the budget constraint, so mathematically it works exactly the same. Again, we assume capital's on the y-axis, labor's on the x-axis, and each of those inputs have a price to them. The price of labor is, of course, the wage being paid. But the price of capital is what we call the rental rate. And essentially, like, it just means that either the firm is renting out the capital or they are or they own the capital and they have an opportunity cost of the rent, like that they could be collecting had they rented out the capital. So that is the cost of the capital. If they only were to use capital, then this is how much they would use given the costs they're willing to incur. The cost divided by the price of capital, which is R, and down here, if they only were to use labor, this is the most amount of labor they'd be able to use, given the cost they're willing to incur divided by the price of labor, which is the wage. And of course, in between, all the points on the ISO cost line represent combinations of the two inputs that will cost the same amount. So suppose a firm spends exactly C on inputs, the cost of labor plus the cost of capital exactly equals, again, a similar relationship to what we saw with the budget constraint, the total value spent on one input into production, which can be considered a good or service, but from the perspective of the firm, right? It's a good that they're purchasing. It's a service they're purchasing from the laborers. And then capital as well, the total value of the capital they can buy, the amount of capital times their price, the amount of labor times their price equals the total cost. So we can obtain a more convenient expression for the slope of and intercept of the ISO cost line by turning this into a slope-intercept form version of the ISO cost relationship. So just doing a little bit of algebra here, dividing the whole thing by R. We'll isolate K and then subtracting W over R times L from both sides will get us to that slope-intercept form for the ISO cost line. So again, here is our y-intercept representing the most amount of capital the firm can use given the costs they're willing to incur, and the slope of the ISO cost line is going to be the ratio of the price of the input into production that's on the y-axis to the price of the input into production that's on the it's going to be the price of the input that's on the x-axis to the price of the input that's on the y-axis. So it's the negative ratio of the wage to the rental rate. It works exactly the same as the slope of the budget line, which was the negative ratio of the price of the good on the x-axis to the price of the good on the y-axis. It also represents the opportunity cost of using one input versus another, which is basically the slope of this line. Using one more input of labor costs negative W over R units of capital along this line. So that's the opportunity cost of using additional units of labor. And then the opportunity cost of using additional units of capital is a reciprocal of that. It works again like the budget line, also like the production possibility frontier you learned about in your introductory econ courses. And it's also the market rate of substitution between labor and capital. It's the rate at which labor and capital can be exchanged within markets, just based on like the prices that are being set for these things in markets that are independent of your production process. So that's what the slope of the ISO cost line represents. The slope of the ISO quant line represents the rate at which you, based on your needs in your production process, can exchange capital for labor in order to maintain the level of output, in order to satisfy your needs. And so once again, it's about interacting those two trade-offs and getting to that optimal point that will minimize the cost for the firm. So just as far as this goes, if the producer wishes to use more of both inputs, more money must be spent. So if they choose to use both more of both inputs, then they have to incur higher costs, which is represented by a higher budget line. ISO cost line, which is a parallel to the original one, because the prices of the inputs have not changed. So when input prices are constant, the ISO cost lines will be parallel to one another. And of course, if the firm is looking to spend less, then it would be represented by a lower ISO cost line. Changes in input prices affect the position of the ISO cost line, much like changes in the prices of goods affected the slope of the budget line. So in this case, if let's say there was an increase in the price of labor, so the wage rate went up, that means the total amount of labor used, given the cost the firm is willing to incur, has to decrease, and so the ISO cost line will rotate inwards. An increase in the price of capital will have the same effect. It'll lower the total amount of capital the firm can use, and so the y-intercept will get closer to the origin, and the budget line will rotate inwards in this way in a counterclockwise fashion. All right, now let's throw everything together and get to that cost minimizing condition. So the ISO costs and ISO quants may be used to determine the input usage that minimizes production costs. So let's say the firm is producing 100 units and they're trying to minimize the cost of producing 100 units. Well, if they were to use the inputs at A, then they would be using a lot of capital and a little bit of labor, and it would cost them this much to do that. But they can obviously do better than that, because again, they can use any combination of the inputs along the ISO quant to yield that same level of output. And there are other combinations that would cost them less. They would be tangent, just touching the ISO cost line that's closer to the origin, representing lower costs. So if the producer uses input mix A, he or she will produce Q1 units of output at C1, but using input mix B will produce the same amount of output at a lower cost, at the cost associated with this ISO cost curve. And therefore, that is the optimal combination of the two inputs that will minimize the cost for the firm. And it's also going to be the point at which the firms, at which the ISO cost and ISO quant lines are tangent, which means that their slopes are equivalent, which means that the marginal rate of technical substitution is equal to the rate at which the inputs can be traded on the open market. So again, recall that the absolute value of the slope of the ISO quant reflects the marginal rate of technical substitution, which is equal to the ratio of the marginal product of labor to the marginal product of capital. And the slope of the ISO cost line is given by the ratio of the price of the input on the x-axis to the price of the input on the y-axis, so the negative ratio of the wage rate to the rental rate. At the cost minimizing input mix B, the slope of the ISO quant is equal to the slope of the ISO cost line, and therefore we have this relationship here. So at point A, we see that the slope of the ISO quant is greater than the slope of the ISO cost. That means that for the firm, an extra unit of labor is worth more to it than they have to pay for it on the open market. And so it makes sense for them to use more labor and less capital, because labor is cheaper at that point. And so they would want to move away from that point. And then over here, the value of an extra laborer is less than the value that they have to pay in the open market. And so labor is too expensive over here, and so they want to use less labor over here. And so this is the point at which the value in the market is the same as the value to the firm of an additional labor. So again, capital is too expensive up here because labor is cheaper over here. So the producer finds it in his or her interest to use less capital and more labor to produce a given level of output. The substitution continues until ultimately the producer is at point B, where the marginal rate of technical substitution is equal to the ratio of the input prices. The condition for the cost minimizing use of inputs can also be stated in terms of marginal products. So again, if we equate these expressions here, which again represent that tangency point at B, the cost minimizing input mix to produce 100 units of output for this firm, and we kind of move things around like we did with the indifference curves and at the optimal consumption bundle, then we get to this condition here that tells us that at the optimal input mix, the amount of output per dollar spent should be equivalent across all inputs into production. So if we are at point A, then the extra amount of output per dollar spent on laborers is greater than the extra amount of output per dollar spent on capital, and so it makes sense to use less capital and use more labor. To minimize costs on a last dollar spent basis, labor is cheaper than capital, and the firm should use less capital at point A. And that, of course, gets us to the cost minimizing input rule for the long run. To minimize the cost of producing a given level of output, the marginal product per dollar spent should be equal for all inputs. So in the long run, the marginal product per dollar spent should be equal for all inputs, and this extends beyond the two input case. It extends to the n input case, however many inputs there are into your production process. At the cost minimizing mix of those inputs, the marginal product per dollar spent should be equivalent across all inputs into production. So this is the condition we were getting to, and this is the long run condition for selecting inputs to minimize cost, as the value of the marginal product of labor equal to the wage and the value of the marginal product of capital equal to the rental rate were the short run conditions for choosing those inputs when one input was fixed. Also, obviously, this is equivalent to this. So both of these stand, and they mean the same thing. Quick demonstration problem to highlight like the value of this relationship and the value of the intuition for managers. So suppose there's a lawn service that Terry owns, and he rents 5 small push mowers and 2 large riding mowers to cut lawns of neighborhood households. The marginal product of a small push mower is 3 lawns per day, and the marginal product of a large riding mower is 6 lawns per day. The rental price of a small push mower is $10 per day, whereas the rental price of a large riding mower is $25 per day. The question is Terry's lawn service utilizing small push mowers and large riding mowers in a cost minimizing manner? So we have to check if the marginal product per dollar spent is equivalent across the inputs, which are the large riding mowers and the small push mowers. So we'll let MPS equal the marginal product of a small push mower and MPL be the marginal product of a large riding mower. If we let PS equal the price of the small push mower and PL be the rental price of a large push mower, cost minimization requires that, again, the ratio of the marginal products to their prices be equivalent across all inputs, in this case, small and large push mowers. So we have to check if that condition is being met. So substituting in the appropriate values, we see that for the large push mowers, if we divide the marginal product of 6 lawns by the $25 per cost per large motor, we see that we get 0.24 there. So that means that each additional dollar spent on a large push mower beyond what's already being used will yield 0.24 lawns being mowed. If we look at the small push mowers, 3 lawns per $10 per small push mower, we see that the marginal product per dollar spent there is 0.3, again, meaning that spending an additional dollar on a small push mower will yield a third of a lawn mowed per dollar spent. And so are we at the optimal input mix here of small and large push mowers? We're not, right? They have to be equivalent. So what should this firm do? I'm hearing a mix of the right answer. Per dollar spent, right? More push mowers yielding more output per dollar spent, and we assume diminishing returns to the inputs, and so therefore, eventually they will equilibrate. Like they will eventually get to that point where they're equal. But yeah, exactly. Because the marginal product per dollar spent is bigger on the small push mowers, then the firm should use more of this and less of this. So the marginal product per dollar spent on small push mowers exceeds the marginal product per dollar spent on large riding mowers. Riding mowers are twice as productive as push mowers, but more than twice as expensive. The firm is not minimizing costs and thus should use fewer riding mowers and more push mowers. So really powerful condition. Even beyond this course, like for any kind of scale operation, like you can use this condition to choose the right amount of inputs in order to minimize your costs. But if you are locked into the short run by one of your inputs being fixed, then comparing the value of the marginal product to the cost of that additional units of that one input will also get you to that cost minimizing level of that input. So long run versus short run important. As always, it's always important. All right, so let's just look at what happens when there's a change in the price of an input. And of course, it's going to lead to a change in the cost minimizing input bundle, which will yield another important principle. So suppose we had that initial ISO cost line FG, and the producer is cost minimizing at A. So they're using K1 amount of capital and L1 amount of labor to produce Q0 units of output. Suppose the wage rate increases. So if the wage rate increases, obviously that's going to increase the cost of labor, which means that with the same cost, you're going to be able to employ a lot less labor at that new wage rate. So that will rotate the ISO cost line inwards towards the origin. The cost minimizing way to maintain the same level of output will then require the firm to spend more. So at this new market rate of substitution, this new ratio of the wage rate to the rental rate, in order to produce the same amount, they would need to spend more, which means the new ISO cost line would be a parallel shift outwards from the origin until it is tangent to our original ISO quant line, representing the new optimal mix of inputs. In this case, more capital, less labor, because labor has become more expensive. So obviously, it makes sense that the firm should substitute away from labor towards capital, because here again now the marginal product per dollar spent is not equivalent across all goods. The marginal product per dollar spent on capital is going to be greater than that of labor because the price of labor has gone up, which means that the relationship between those is now less, between its marginal product and its price are less now. So it makes sense for the firm to substitute away from labor to capital, to getting them to this point, which will once again equilibrate the marginal rate of technical substitution with the new market rate of substitution. That's again embodied by the slope of the ISO cost line. Yeah.
I'm confused by the parallel.
The what? Which one?
Where you said there's a new parallel shift. So F and L2.
I'm sorry. FH. L2 is the amount of labor. Yeah.
H and then I and
IJ. Yeah.
IJ.
Yeah. So labor got more expensive. The firm wants to continue producing that same amount, so they have to spend more. So they increase their costs. Yeah. So they increase their costs. So that's what the parallel shift of the ISO cost line represents. But now it's tangent at a new point, representing, that new.
I got confused that they want to still produce the same amount. I thought it was attached to the new ISO cost line.
It couldn't be.
If they want to keep it up there, then
it couldn't be, because this is kind of like their budget constraint, right? So this would be infeasible based on what they're willing to spend over here. They would have to produce less output. Yeah, there would be an ISO quant line closer to the origin, representing a lower amount of output. Yeah. So the producer substitutes away from labor toward capital and adopts a more capital-intensive mode of production. Again, meaning that they're using more capital relative to how much labor they're using. So it becomes more capital-intensive. Versus over here, they were using a more labor-intensive production mix. So that gets us to the principle of optimal input substitution. To minimize the cost of producing a given level of output, the firm should use less of an input and more of other inputs when the input's price rises. Pretty intuitive, but the model can predict that same intuitive result as well. All right, now let us jump to the cost function, where all of this was going. So for given input prices, different ISO quants will entail different production costs. Since the cost of production increases as higher ISO quants are reached, it's useful to let C of Q denote the cost to the firm of producing ISO quant Q in the cost minimizing fashion. So when we're looking at cost as a function of quantity, we're assuming that the firm is optimally choosing their input mix to minimize their cost of production. They're always at that point of tangency between their ISO cost and their ISO quant. So the function C is called the cost function. The cost function reduces the amount of information the manager has to process to make optimal output decisions. All right, so once again, of course, we have to consider costs in the short run versus the long run. So in the short run, we know that there are there is at least one input fixed. And so because that input is fixed, then there's going to be a fixed cost associated with that input. And then there's going to be a variable cost associated with the variable input. So therefore, total cost in the short run will be equal to fixed cost plus variable costs. Again, fixed costs denoted in this case FC are costs that do not vary with output and include the cost of fixed inputs used into production. So the amount of the lease for the factory for 3 years is your fixed cost. The amount you paid for your assembly lines that you use in your factory is a fixed cost. Variable costs, VC of Q, are costs that change when output is changed and include the cost of inputs that vary with output. So they are going to be a function of quantity because, as we know, in order to increase the amount of output, you need to increase your variable input. That's the only way you can do so, and thus your variable cost will be changing as your output changes. The short-run cost function summarizes the minimum possible cost of producing each level of output when variable factors are being used in the cost minimizing way. So when we're talking about variable factors being used in the cost minimizing way, we're again talking about factors being chosen at the level where their value of their marginal product is equal to their price. All right, so here tabularly is just a cost function that we can examine. As the first case, again, we start from a discrete case in tables and we jump to the graphs to gain the intuition that tells us the relationship between the relationships we're studying, and then we jump to the math. So here's the table. We have a fixed input, 2 units. The fixed cost is $1,000 per unit, so it's going to be $2,000 regardless of the amount of output that's being produced. We've got a variable input, which again is going to be what will determine how much output we can produce. It's labor, of course. So going from 0 to 1 labor, our output goes from 0 to 76 units, so the marginal product of labor is 76. Going from 1 to 2 units, the overall output goes from 76 to 248. So the marginal product of labor is the difference between those two. The variable cost is the wage that's being paid. We just assume it's $400. And so for one laborer, the cost is $400. For 2 laborers, it's $800, 3, $1,200, and so on and so forth. And then total cost is, of course, the sum of fixed cost plus variable cost. And so at any given level of our output that we're producing, it's going to have some portion of that be due to the fixed cost. So for 248 units of output, there's going to be, of course, that fixed cost of $2,000, which is not changing, plus the $800 to pay for the wages for laborers, which is our variable cost. So fixed cost $2,000 plus variable cost $800 equals total cost of $2,800, and of course that relationship holds as we increase output. All right. So the shape of the total cost curve is going to reflect the nature of the production process, the nature of the general production process that we have been tracking, and again is the basis of all intuition in business because it is the most common case. And any case you might have that deviates from it can be compared to it, and so you can have the intuition for the basic common case and then kind of let that inform, well, how should I change given my situation is slightly different from the common case. So this is the starting point for your basic intuition. So remember, we starting out 0 people, you hire 1 person, they start doing everything, you hire a second person, they start dividing up the tasks, so there's specialization. So there's increased efficiency in production. So initially, each additional person is producing more than the prior person. So the marginal product of labor, the extra amount of output, produced by employing additional units of labor is increasing initially. So you have increasing returns initially. That means that each additional unit of output is going to cost less than the prior unit because, again, you are hiring people at the same rate, but they are producing more than the prior person, and so your costs are going down. And so your total costs initially are increasing, but the extra cost of producing additional units is decreasing along this range here, which is the marginal cost, which I'll talk about in more detail in a bit. But it is the slope of the total cost function. Again, it represents the extra cost incurred by producing one additional unit, the marginal cost. So the marginal cost is going to be decreasing initially over the range where the marginal product of labor is increasing due to increasing returns. And then, of course, once the firm hits that short run wall and they hit that diminishing returns range of production where, there's not enough factory space to go around, but they need to hire more people because they want to produce more output, then each additional person will produce positive amounts of output, but they'll produce less than the prior person hired. They'll have diminishing returns. The marginal product of labor will be diminishing. It will be less for each additional person hired. That means that the extra cost of producing additional units will start to increase. That means the marginal cost will start to increase at that point due to diminishing returns, and therefore the total cost function will start to increase at an increasing rate. So the slope will start to increase, again representing the marginal cost, the extra cost of producing additional units, and so that's why we see this turn happen in the total cost function. Total cost is a difference between, is the sum of fixed cost plus variable cost. Fixed cost is not going to change. And so fixed cost is just a line at whatever that fixed cost is, regardless of the amount of output. It is constant over the short run. But variable cost is the thing that's changing, and variable cost is the thing that's being affected by the nature of the production process, increasing returns, decreasing returns. It is what is defining the nature of the cost. And so therefore you will see the variable cost curve be basically just a translation of the total cost curve translated down the distance of fixed cost. So at any given level of output, the difference between total cost and variable cost graphically is going to be the fixed cost. But again, the variable cost curve will have the same shape as the total cost curve. All right, now let's talk about the relationship between average and marginal cost. So we talked about the relationship between marginal product and average product, where marginal product would bring up average product. If it was above it, they would be equivalent at the point where they meet, and then marginal product would bring down average product after that. Again, we're talking about additional units of output being produced by employing additional units of the input. And if you on average are producing a certain amount at the level of labor, and then your marginal product is above that, by adding one more person, they're going to produce more than the average. Is going to bring the average up, and that's where that relationship comes in. That relationship will be mirrored in the relationship between average and marginal costs, and the intersection and relationship between those costs will be super important for the decisions that the firm makes to maximize profits in the varying market context that we'll consider. So it's important to kind of understand the connections, where they come from, why they are what they are, and their significance, both in production and how that translates to costs. One common misconception about costs is that larger firms have lower costs than smaller firms because they produce larger quantities of output. What individuals most likely have in mind when they consider the advantages of producing large quantities of output is that the overhead is spread out over a larger level of output. The overhead is the fixed cost. It's what the firm needs to set up shop essentially in order to operate at the level they want to operate at, and we know that level is fixed, which is what defines the short run, but certainly during the short run. And so you have a fixed amount of money that's being spent on that input, and so if you look at the average fixed cost, the average amount of that cost that is attributable to the cost of producing additional units, as the firm gets bigger and bigger, that cost is going to get smaller and smaller because you have a number that's not changing being divided by a number that's getting bigger and bigger and bigger, and that's going to spread out the fixed cost as the firm gets bigger. And so the firm gets to enjoy the benefits of that. So again, this number that we look at to sort of highlight that important property is the average fixed cost. It is defined as the fixed cost divided by the number of units of output. So again, you have some fixed costs in the short run, defining your short run, divided by quantity as the firm decides to increase its scale as much as it possibly can within the limitations of the market it operates in. Then that fixed cost is going to be spread out more and more and more across all the units being produced. And of course, if there's average fixed costs, there have to be average variable costs. What is the average amount of my variable input that is attributable to the extra cost of producing additional units of output? Well, it's my average variable cost. It's my variable cost divided by the number of units produced. So it's my variable cost divided by Q. And of course, if you throw them both together, you're going to get your average total cost. That's my average cost of producing units at the scale that I'm producing. And that's going to be an important number as well as we move forward. And it is the sum of the average fixed cost plus the average variable cost. Any questions yet? All right. So here we have yet another table representing our cost function, reflecting our production process that we've been assuming to be the most common, but adding in the average costs in there to kind of see what's happening to them as the scale is increased due to the nature of the production process. So again, you got that fixed cost, you've got the variable cost, still $400, and then output is changing the same way that we've assumed it was changing. Total cost again being the sum of variable cost plus fixed cost. Average total cost, sum of average fixed cost plus average variable cost. So for 76 units, we've got our average fixed cost, which is 2,000 divided by 76, which is 2632. We've got our average variable cost, which is 400 divided by 76, which is 526. And then we've got the sum of those two, which is the average total cost, which is the sum of 2632 plus 526, which is 3158. So we see that as output is increased for this firm, that the average fixed cost is becoming less and less and less, and that's because, again, we have what's called a spreading effect of that fixed cost as a result of increasing scale. So the bigger the firm gets, their overhead on average becomes smaller and smaller with respect to the individual units that they are producing. So this number is always going to be going smaller in the short run until the firm realizes we need to buy more capital and therefore get into the long run. But as soon as they buy more capital, they are once again in a short run situation, which we'll talk about in a bit. So that's what's happening with average fixed costs. It's always going to be pulling down the average total cost as the firm gets bigger and bigger. Average variable cost, the story is a little bit different though. Over the range of increasing returns, where the variable costs are going to be increasing but at a decreasing rate, the average variable costs are going to be going down. So we're going to go from 526 to 323 to 244 to 204 to 182 to 169, 164, and then it kind of levels out there. It kind of bottoms out there. And it bottoms out at the point where the firm hits that decreasing returns to scale wall due to the short run, due to the limitations of having only so much capital for their workers to work with. And so because of that, the average variable cost then starts to go up after that. It's not significant in this table, but it does happen from 169 to 182 there. 164, then goes to 169, goes to 182. In terms of what's happening to average total cost, well, over the range of increasing returns, where average variable cost is going down, you're going to have both average variable cost and average fixed cost driving down average total cost. So average total costs are going to be driven down as the firm gets bigger and bigger over the increasing returns range by both of these forces, both the spreading effect and the increasing returns effect of the average variable cost. even though at this point the diminishing returns uh, start to bring up average variable costs, the spreading effect still dominates, at least for this level of production, which is 21, 24 units of output, and that means that average total cost will still be decreasing, even though average variable costs will be increasing. But eventually, the average variable cost, due to the diminishing returns, will start to overpower the spreading effect of the average fixed cost, which will start to bring up average total cost. And so average total cost will also have that U shape, will bottom out at a point, but it'll bottom out at a point after the average variable cost bottom out. And then it will start to increase as well, due to the diminishing returns effect being so dominant and overpowering the average fixed cost effect. So let's look at that whole thing again, but graphically. Oh, actually, after we look at marginal cost. That's right, I need to establish marginal cost formally. So marginal cost is the cost of producing an additional unit of output. That is a change in the cost attributable to the last unit of output. So it's the change in cost with respect to the change in quantity. So here we've got our marginal cost. So marginal cost is, like I said earlier, it's going to be decreasing along the range of increasing returns to labor. But as soon as we hit that diminishing returns to labor, then marginal cost will start to increase. And so that'll start bringing up total cost at an increasing rate. When only one input is variable, the marginal cost is going to be the price of that input divided by its marginal product. So there is an inverse relationship between marginal cost and marginal product, which is why we have that kind of like that mirrored quality to the cost function from the production function. The same properties kind of affect them in the opposite way, right? Marginal cost is increasing when marginal product is decreasing, and then marginal cost is decreasing when marginal product is decreasing, and then marginal cost is increasing when marginal product starts to decrease over the diminishing returns. So marginal product increases initially, reaching a maximum and then decreasing. Given that marginal cost is a reciprocal of marginal product times the input's price, it decreases as marginal product increases and increases when marginal product is decreasing. So again, just re-emphasizing the fact that there is that inverse relationship between marginal product and marginal cost. All right, now let's look at everything graphically. So marginal cost is going to decrease, then increase. So it's going to have kind of like a swoosh shape, kind of like that Nike swoosh shape. So this is like your standard marginal cost curve. Again, this is happening because of increasing returns, then it bottoms out, then we have diminishing returns, which start to drive up the additional cost of producing additional units. So the series of figures will depict the curves in the continuous case. Again, tables are discrete cases. Continuous cases can be represented graphically, and they represent cases in which the quantity is infinitely divisible, meaning we can have decimal quantities versus just integer values that we see in the table. So here is our average variable cost curve. The average variable cost will decrease and then hit its minimum and then start to increase. At the point it hits its minimum is the point at which the marginal cost curve will cross. So over this range here, we have those increasing returns, which are bringing down our average variable costs. And again, like, the average is going to be dependent on the additional units, the cost of the additional units. So here's where we hit that diminishing returns wall because of the short run. But again, there's going to be that small range over which the marginal cost is going to start to increase, but because it's still below the average variable cost, it will still bring down the average variable cost initially, and then once they're equivalent, marginal cost will supersede it, and each additional unit will cost more than the average, which will start to bring the average up. Here's our total cost curve, again U-shaped, and its minimum occurs to the right of the average variable cost curve. So notice that the average total cost minimum is to the right of the average variable cost minimum. So again, the average total cost curve is being affected both by the average variable cost and the average fixed cost. The average fixed cost being the distance between the average total cost and the average variable cost. And we know that average fixed cost is always going down. There's always a spreading effect acting upon the average total cost of producing. And so even though the average variable cost starts to be pulled up due to diminishing returns once marginal cost crosses it, the average total cost will still be the dominant effect up until this point here. So average total cost will continue to bring down, average fixed cost will continue to bring down average total cost even after diminishing returns starts to bring up average variable cost. But there will be a point where that will change, and the diminishing returns effect will start to dominate, and that will start to pull up the average total cost curve. What's bringing up the average variable cost curve will eventually start bringing up the average total cost curve, and the spreading effect will no longer be like the dominant force working upon the average cost of producing. And that will happen at the point where marginal cost crosses average total cost and starts to bring up the average total cost. All right. Just a quick note on fixed costs. We may have talked about sunk costs. I think we talked about sunk costs in the first chapter. Sunk costs are costs that cannot be retrieved at the time that decision is being made. It's essentially spilled milk, and there's no sense crying over it. So a sunk cost is a cost that is lost forever once it's been paid. Imagine you are the manager of a coal company and have just paid $10,000 to lease a rail car for 1 month. The amount of the $10,000 that is a sunk cost depends on the terms of your lease. If the lease does not permit you to recoup any of the $10,000 once it's been paid, then the entire $10,000 is a sunk cost. If the lease states that you will be refunded $6,000 in the event that you do not need the rail car, then only $4,000 of the $10,000 is a fixed cost. In fixed cost is a sunk cost. Since sunk costs are lost forever once they've been paid, they are irrelevant to decision making. So that just gets us to this important but quick principle of irrelevance of sunk costs. A decision maker should ignore sunk costs to maximize profits and minimize losses. All right, now let's jump to the algebraic form of cost functions. In practice, cost functions may take many forms, but the cubic cost function is frequently encountered and closely approximates any cost function. It will have the properties that we're looking to have in our cost function. It will reflect the nature of the production process that's very general. So the cubic cost function is given by this expression here. So you're going to have some constant term plus these terms that are going to have the variable quantity in there. So we know that F has to represent the fixed cost. It is the cost that is independent of the quantity of output. And so that term is the fixed cost of production. And so therefore these three terms will represent the variable cost of production. So we know that total cost is equal to fixed cost plus variable cost, and so thus any component that does not include the variable in it will not be variable and therefore will represent the fixed cost, and any term that does have the variable in it will represent the variable cost. Given an algebraic form of the cubic cost function, we may directly calculate the marginal function by taking the derivative. So this is where people start to make mistakes in this course that aren't plugged into the course, because the book will just give you an equation for the marginal cost, and it basically assumes that you're going to memorize it versus just take the derivative of the total cost function and get the marginal cost. So make sure that you're not memorizing equations. You're understanding how to get to the equations from the equations you are given, because that's what you will be expected to do. And it's not a difficult process. I went through derivatives last time, if that's something you're a little rusty with. So, I caught people up. That's the whole point of that whole thing. And now we are ready to take derivatives, so you should be taking them, and that is it. I don't want to see anybody posting anything on Piazza before the next exam. Can I have a sheet with all the equations on there? No, you can't. You don't have to memorize anything. You have to do math, which is what's expected of you in this class. That's why there's a prerequisite. I'm not talking to everyone that's sitting here, of course. I'm talking to everybody in the class, so, and everybody's here. All right, so given this cost function, we take the derivative to get marginal cost, right? The derivative of a constant is equal to 0. The derivative of this is equal to what? What's the derivative of this? 2bq. And what's the derivative of this? 3cq squared. Excellent. So our marginal cost is equal to a plus 2bq plus 3cq squared in the very general marginal cost formula. But I'll never ask you to do things generally. You'll always have specific examples, of course. All right, demonstration problem. The cost function for managerial enterprises is given by this cost function here. What is the fixed cost of production? What is the variable cost of production? 3q squared, right? 3q squared. All right, we're going to determine the marginal cost, the average fixed cost, the average variable cost, and the average total cost when Q equals 10 units. So what is the marginal cost of production here? Not when using 10 units, just in general. 6Q, right? It's just the derivative of our cost function with respect to quantity. The derivative of this is equal to 0. The derivative of this, you multiply the whole thing by 2, subtract 1 from the exponent. All right, so that's our marginal cost. We plug in 10 units to get our marginal cost, which means that producing an additional unit, the 11th unit will cost $60. That's what our marginal cost is telling us. Average fixed cost. So what is the average fixed cost of production here? Gesundheit. 20 over 10, which is equal to 2, right? So we've got our fixed cost, which is 20, divided by 10, which is our quantity. So the average fixed cost of production is $2. So when you're producing 10 units, the amount of each unit on average that's attributable to your fixed cost is $2. Average variable costs. So we're going to take our variable cost, we're going to divide that by Q, right? So we're going to get 3Q multiplied by 10 equals $30. So on average, when 10 units are being produced, $30 of the cost to produce each unit is attributable to the variable input, which is labor. Average total cost. How much is average total cost? $32, right? It's the sum of average variable cost plus average fixed cost. Any questions on this? All right, there'll be some more practice in the homework, of course. All right, now let's turn to long run costs. So in the short run, you are, again, limited by the fact that there's a fixed factor of production, which leads to decreasing returns, which leads to average total cost having that U shape, eventually being driven up if you want to increase your scale. So in the long run, though, all costs are variable because the manager is free to adjust the level of all inputs. So just imagine you're on some average total cost curve, reflecting some amount of capital, and you're producing, let's say, Q naught units of output. This is your average total cost of production. Things are going really well. Folks are buying a lot of your stuff. You want to sell more. You increase the scale of your output, but the only way to do that is to move along your average total cost curve because you're locked into the short run. And so you do increase your output to Q1 units, but your average total cost of production increases quite a bit. So that starts to eat into your profit margin. So then you start to think, okay, I need to change the size of my factory. I need to get another assembly line. I need to buy more capital. It's the long run. You're able to do that. You do that. As soon as you do it, you're in a new short run situation. So let's say you're in this short run situation. This short run situation represented by this average total cost curve, and therefore producing Q1 units of output now costs you that much. The average total cost has dropped dramatically because of the investment you made. Great. Now your profits are shooting up. That'll cover the cost of your overhead for your new capital. Things are going great. Market booming. People buying stuff. So you want to increase your scale of output. So you do. So you continue producing more, and you move along your average total cost 1. Now you're in that second short run situation with that new level of capital. But now, when you're producing Q2 units of output, your average total cost has skyrocketed to average total cost 1 of Q2, significantly higher than it was before. Once again, it's been a few years, things are going well, but your costs are being eaten away by your limitations of the short run, and so you decide it's a long run time again. I'm going to invest in more capital once again. And so you do. And so you get a lot bigger now. And now you're on this average total cost curve. You've minimized the cost of producing that level of output, Q2. Now you're only paying on average ATC2. But we do see that the minimums do first go down and then go up in the long run. So in the long run, it's not like you're always going to benefit by getting bigger and bigger and bigger, and that's going to depend on the nature of the industry you're operating in. So the long run average cost curve is going to be denoted LRAC, defines the minimum average cost of producing alternate levels of output, allowing for optimal selection of all variables of production, both the fixed and variable factors. So the long run average cost curve is the lower envelope of all the short run average cost curves, and it is this red kind of warped long run average cost curve you see there. This means that the long run average cost curve lies below every point on the short run average cost curves, except that it equals each short run average cost curve at the points where the short run curve uses fixed factors optimally. All right, now let's talk about what this means in terms of the long run. Why are costs going down and then going up? All right, so the nature of long run average costs can be reflected by the idea of economies of scale. So the U-shape of the long run average cost curve implies that initially an expansion of output allows a firm to produce at lower long run average costs, as is shown for output between 0 and Q star. So in the long run, if they're able to change their output to the extent they want to, then the firm can get bigger and bigger and benefit from that by decreasing average costs over a certain range. This condition is known as economies of scale, and essentially it's also known as increasing returns to scale as well. It means that there are long-run average costs that are going down as the firm is getting bigger. When there are economies of scale, increasing the size of operation decreases the minimum average cost. After a point Q, such as Q star, further increases in output lead to an increase in average cost, though. This is known as diseconomies of scale. So over this range here, the firm experiences diseconomies of scale or decreasing returns to scale as the firm starts to get too big. Sometimes the technology in an industry allows a firm to produce different levels of output at the same minimum average cost. And so the long run average cost will not change, and there'll be what's called constant returns to scale. So average total cost will not be changing in the long run for firms in this kind of an industry. So what explains the scale effects in production? The answer lies in the firm's technology of production. Increasing returns often arise from increased specialization. As a firm gets bigger and bigger, the larger scale of operation means that individual workers can limit themselves to more specialized tasks, becoming more skilled and efficient at doing them. So there's a limit to it, but it can happen on a really huge scale where a firm can get so big that like each individual person is like being used with precision on some individual tasks. It's making the overall efficiency of the firm smoother, better, and lowering costs. Another source of increasing returns to scale is very large initial setup costs. So if the firm has huge setup costs, in order to just set up shop, the operation is enormous, then you're going to have a fixed cost that's going to be spread out over a huge range of production. And so you're going to have a dominant spreading effect, bringing down average costs over a long range, which may just be the relevant range of output. And so average costs will be the lowest possible for these firms, but they need to get extremely huge to enjoy that kind of benefit. A third source of increasing returns is network effects. So when you have network effects in an industry, the good that's being used has more and more value as more and more people use it. So you think about Microsoft Windows. Windows is just some operating system. Anybody can create an operating system. But the fact that everybody uses Windows pretty much, besides like Mac users and Linux users, and it's basically included in every single computer that's sold aside from those others, the more the people use it, the more valuable the item gets, the more the firm can get bigger and ultimately lower their costs. At this point, their marginal cost of producing additional units of Windows is like almost nothing to the firm, to Microsoft. So they get to enjoy those increasing returns to scale because of network effects. Decreasing returns to scale is the opposite scenario, typically arising in firms due to problems of coordination and communication. Firms can get too big. Imagine two huge firms, multinational conglomerates, merging. You have huge amounts of departments. You have huge egos at the top, people that are just not able to synergize, get together, and make it into a smooth running operation. If firms get too big, you're going to have those problems, and you're going to have those decreasing returns to scale. Average total cost, long run average total cost will start to increase in the long run as a result of that. Although increasing returns induce firms to get larger, decreasing returns tend to limit their size. So the nature of this long run average cost of the industry will dictate how competitive the industry can be. If there's scale effects, increasing returns to scale for an industry, then you're going to have a lot of large firms in that industry. Large firms means not much competition. So the relationship between long-run average costs and how competitive a firm is pivotal. All right, folks, we're done with this section. Have a good weekend, and I will see you guys on Tuesday.